So chapter 9 builds on chapter 8, just like every other chapter in this course seems to build on the earlier ones. In chapter 8, we talked about chemical composition and we talked about individual molecules and determining the empirical and the molecular formulas for those. We're now going to move into not just individual molecules, but into chemical equations. And so as we move into this, we're going to be dealing with chemical reactions or chemical equations and using all of the stuff that we did in the chapter that came before. So mostly this using molar mass as a conversion factor. This is something that is measurable in the lab, but this is a central concept in chemistry. So that's a really important thing that comes forward as we move into chapter 9. So chapter 9 is technically on stoichiometry. It's a really fun word to say. So stoichiometry is the study of mass relationships in chemical reactions. Again, because we can measure mass in the lab in grams, and we do have that central idea of the mole, we're going to put it all together with stoichiometry and chemical reactions. So a balanced chemical reaction or a chemical equation is the key piece of information that we need. That relates different amounts of reactants and products to each other. And so amounts can be talking about different things. Amounts could be talking about a mass, but it could also be talking about a mole. And again, as the mole is the central concept in chemistry, that's where we're going to start. So this is a chemical reaction. It's a chemical reaction where hydrogen gas and nitrogen gas combine to form ammonia. You can see that you can graphically or pictorially represent that. And as we balanced it with those numbers out the front, we did so that we weren't creating or destroying atoms of these different elements. We could talk about it as how many molecules interact with each other. So those coefficients are 3 molecules of hydrogen, 1 molecule of nitrogen, making 2 molecules of that NH3. We're going to take this one step further and, like I keep saying, bring it all back to that central concept of the mole. And so in all of these, if we have a balanced chemical equation, that is the key to our understanding stoichiometry. So here we have a chemical equation. We have that awkward place of it being odd and even. So I'm going to even up my number of oxygens and then go from there. I was just pausing as I mentally balanced that. Those coefficients, and when there's nothing, it's understood that there's a 1. Some of you are filling a 1 in when there was nothing there. This tells you how many molecules are interacting. So in this case, we have 2 molecules of nitrogen monoxide, 1 molecule of oxygen gas, and 2 molecules of nitrogen dioxide being formed. We could scale that up. That's always another fixed ratio. It's a fixed ratio of interaction between the reactants and the products. Sometimes we call it between the species or the things in the reaction. Our X is for reaction. So we could scale it up. If you had 200 molecules of nitrogen monoxide, we'd need 100 molecules of oxygen. I'm just adhering to the proportions here, and that would make 200 molecules of nitrogen dioxide. We could scale it backwards, right? If we don't know how many molecules of the reactants we have, but we have 10 molecules of the nitrogen dioxide forming, what we could say is, okay, well, it would be half of that for the oxygen and the same amount for the nitrogen monoxide. In all of these, it gives us a recipe for what are the proportions, what are the fixed ratios. So you might think of it as proportions, or the fixed ratios between the things in the reaction. If we think of it this way, if we have N molecules of this, we'd have 2N of that and 2N of this. All of it is adhering to those fixed proportions, that ratio of interaction between the different species in a chemical reaction. Here's the kicker. If we said that N was Avogadro's number, now all of a sudden we're not talking about individual molecules, but we're talking about moles. And again, in this, if it's a central concept, that's where we're going to go. So we can see those numbers out in front, those proportion, those fixed ratios between the different species being represented as moles. And so again with this one, if it was all balanced and the coefficients didn't come down with us, right? Those are the original coefficients from our balanced chemical reaction. Now all of a sudden we're talking about a whole lot of molecules. They're still going to interact in this fixed proportion. So we would have 1 mole of oxygen making 2 moles of nitrogen dioxide when it reacted with 2 moles of the nitrogen monoxide. Those coefficients in the equation are mole-to-mole ratios for the reactants and the products. And that is really where we kick off this chapter of stoichiometry and chapter 9. So let's practice some mole-to-mole ratios. So 9.2 talks about mole-to-mole ratios, and these mole-to-mole ratios are really the coefficients as a unit conversion. So you're going to use your coefficients as a unit factor. We're going to continue the problem-solving strategy of dimensional analysis because this allows us to piggyback on what we've already done with our dimensional analysis already. So here we have an example of propane burning. It's a combustion reaction, a redox reaction. It's already balanced for us. You have to always double check that it's balanced. And here you can see it's 1 mole of propane reacting with 5 moles of oxygen, making 3 moles of carbon dioxide and 4 moles of water. So in this one, it says how many moles of oxygen are needed if we have 2.5 moles of propane. So always with dimensional analysis, you're going to start with what you know, which is this number over here. And then in order to get to where you're going, you're going to use the coefficients of those things that you're talking about. So we're wanting to go to the number of oxygen. So sometimes it's nice to map it out. So we've got, I'll just change colors so you can see it a bit better here. We'd have 2.25 moles of this, and we want to know how many moles of that. And so start with what you know. You're going to put the moles of propane down below, and that number is the coefficient from the balanced chemical equation. Where you're going goes on the top, same as we've always done with dimensional analysis. In this case, it's moles of O2 are where we're going, and the coefficient there is the 5. And so you can see, same as always with the dimensional analysis, the units cancel and allows us to see the math for what we should be doing. We would get our 11.25 on our calculators, and then we would round to 3 sig figs because that's what we were given from the beginning. The mole-to-mole ratios are like numbers from counting. They don't limit our significant digits. Okay, so in this one, and I might just erase the work off that balanced chemical equation because I do find it handy to use as a bit of a roadmap for figuring out, okay, what do we have and what are we looking for? So this next question down below here says, if we have 3.5 moles of oxygen, how many moles of carbon dioxide are going to be produced? And so we could scribble that underneath here if you wanted to. You don't have to map it out like this, but sometimes that's handy because we're moving around in the chemical reaction. So we know we have 3.50 moles of oxygen, but we want to know how many moles of CO2 or carbon dioxide are going to be produced. So always with dimensional analysis, start with what you know. Be really cognizant of your units because that really is the key to everything. We don't want to talk about moles of O2. We want to talk about moles of CO2. And so you can set it up with your dimensional analysis pattern of the zigzagging. And again, those numbers are going to come from the balanced chemical equation. So there's a 3 as a coefficient in front of the CO2, and there is a 5 as a coefficient in front of the oxygen. This is one of the first times, oh, yeah, that's right. Sorry, I was just distracted for a minute there. So this is the first time that we see not just a 1 somewhere. So if you remember, I always say, if it's on the top, multiply by, and if it's on the bottom, divide. The moles of O2 are going to go away, and that leaves us with moles of CO2. Oops, In this one, we're going to round for 3 sig figs. And so if I put in 3.50 times 3 and divided by 5, I should get 2.10 as my answer. Moles of CO2. And again, it's really handy to be able to see this balanced chemical equation as the tool. And so it can be handy to use that as a bit of a map. I'm going to lose this as I scroll to the next one, so I will set it up before I get too far ahead of myself. The next question says, how many moles of water would form if there's 4.50 moles of CO2 formed? So 4.50 here, and it says how many here? And so always, I'm going to scroll, sorry. I'm going to start with what I know. So that's 4.50 moles of CO2. I don't want to talk about moles of CO2. That's what I want to cancel out. I want to talk about moles of H2O. And I find those numbers from that balanced chemical equation. So there's a 4 in front of the water, and there's a 3 in front of the carbon dioxide. I would now use my calculator, punch in 4.50 times 4 divided by 3, and round to 3 sig figs for 6.00 moles of H2O. Last one, give it a shot. I'm going to start with what I know. I can set up a whole lot of stuff without even doing any sleuthing back to the chemical equation. In this case, I pull those numbers again from the balanced chemical equation and follow through, rounding to the 3 sig figs for how many moles of propane are actually going to be burned when 2.5 moles of carbon dioxide are produced. And that's really the way that we're going to keep going with this dimensional analysis, now rolling in the mole-to-mole ratio.